Chapter 10, Liquid, Solids, and Phase Changes. At the end of last semester, we were discussing the behavior of gases. So we'll start this semester by looking at liquids and solids. So really we're going to study the different properties when a gas goes to a liquid, liquid goes to solid, and vice versa. So what happens when a phase change occurs? And phase changes are always physical changes. You are not changing the composition of what is present, just how close the particles are, how fast they're moving, looking at volumes and shapes as well. So when we talk about liquids, it's important to discuss intermolecular forces. But first we have to talk about intramolecular bonding. And we've discussed this. Intramolecular bonding is ionic bonding or molecular covalent bonding. So intra means within the molecule. So these types of bonds have a lot of energy, a lot more energy than what happens with interactions between molecules. So here we're looking at sharing electrons, or if we're looking at ionic bonds, then the complete transfer of an electron from the metal to the nonmetal, and then bonding occurring because of the opposite charges that occur. So inter, once again, means between the molecules. So this is just how attracted is one molecule to its neighbor, okay? Water, for example, we'll study this. Water itself has covalent bonds. That is the intramolecular forces. It's covalent. Sodium chloride, that's a salt, and it has ionic bonding. It's intramolecular. But how would sodium chloride, when we dissolve it in water, react? Or how would those molecules and ions associate with each other? And that association between molecules and ions, or molecules and molecules, are those intermolecular forces. So we're going to study ion dipole, dipole-dipole with a specific type of dipole-dipole interaction called hydrogen bonding, and then London dispersion forces. And all of these forces can be categorized simply as what we call van der Waals interactions. So first we have to figure out what is a dipole moment. We have polar covalent bonding, and we discussed this when we looked at electronegativities and electronegativity differences. And recall that if the difference is less than 0.5, we would say it's nonpolar. It's a nonpolar bond. If it's between 0.5 but less than 2, it's polar covalent. And if the electronegativity difference is above 2, anywhere from 2 to 4, then we would say it's ionic bonding. But there is that sliding scale. So here, in looking at hydrofluoric acid, we see this is an electrostatic potential map, that the electrons are mostly residing around the fluorine. Fluorine has an electronegativity of 4. Hydrogen is 2.1. So the difference there is 1.9. So this is a polar bond, meaning that the electrons are mostly towards the fluorine atom, making it slightly negative, making this hydrogen slightly positive. So then we end up having two poles, one pole that's positive and one pole that's negative. Hence dipole, di meaning two, like the North Pole and the South Pole. So we have our electron-rich region, we have our electron-poor region. And remember, electrons are negative, so where there's more electrons, that side's more negative. Where there are less electrons, that side is more positive. And we indicate that with our sigma symbol here, sigma meaning slightly negative, here meaning slightly positive. If we just put a positive and a negative sign, that would mean that it is that charge. It has actually lost the electron or gained the electron. And that's not what's happening here. We have not transferred electrons. We are just sharing those electrons, but we're sharing them unequally. It's like a tug of war, and here fluorine is winning. So once again, just to review, the electronegativity is different than electron affinity. Remember, electron affinity is measurable, and you're looking at how much energy is associated with an atom picking up an electron. Sorry, this X minus should be on the other side of the arrow. Chlorine has the highest electron affinity. Electronegativity is an arbitrary scale which just says how much does an atom pull on electrons within a bond. So electronegativity and electron affinity are two different things. But we use electronegativity to assign whether or not molecules are going to be polar or nonpolar. And since electronegativity is relative, we see that fluorine is the highest value. Remember, those values are all on your periodic table that will be given to you. And here we have a periodic table that is listing those electronegativity values, so you're more than welcome to look at this. Keep in mind, the least electronegative atom is down here, francium. Most electronegative up here, fluorine. So nonmetals are more electronegative because they want electrons more. Metals tend to be less electronegative because they'd really like to give up their electrons. So if we're in these bonding situations, that's why we see those electronegativity differences being so large between metals and nonmetals, where that nonmetal has so much strength to pull the electron away it can. Mostly, though, we're concerning ourselves when we are looking at electronegativity differences and assigning polar or nonpolar. Those are for covalence. So we're going to be staying on this side of the table and just looking at our nonmetals. So if we compare ammonia and nitrogen trifluoride, here we have ammonia. Nitrogen has a larger electronegativity than hydrogen. So it's pulling hydrogen's electrons towards it. Keep in mind, this is a trigonal pyramidal shape, and this is important. So you want to go back and review how to draw your Lewis structures and how to assign shapes. Because in class, I'm going to give you a flow chart into how we can actually assign, is this polar or nonpolar. I feel it's the easiest way to decide. So because nitrogen is pulling the electrons towards it, the overall dipole moment, and this is vector math, you don't have to worry about it, but we can imagine if we're pulling all towards nitrogen, the overall dipole moment then is going up in this direction. And where we have this positive sign, that means where we are electron poor, the arrow points to where the electrons are, or where it is electron rich. So we look at the electrostatic potential map, and we see, sure enough, the red zone means there's a lot of electrons. The blue here shows not a lot of electrons. So nitrogen is pulling those electrons. This is a polar molecule. Now we have the same shape. This is still trigonal pyramidal. Why? Because we have 3 atoms, but 1 lone pair. That's a 3-1-4. But now fluorine is pulling the electrons away from nitrogen, so out along the skirt, if you will. So we see that down here where the red regions are on the outside, okay? The overall resultant dipole then is actually going down. So both of these molecules are polar, but in opposite directions. We would still assign them as these are polar molecules. So looking at polarity and dipole moments, and when we study this, you have to take into consideration the shape of the molecule, and you'll see that most often, if a molecule has a lone pair of electrons, unless it's linear, we'll see that it's a polar molecule. Now, if it's linear, it will be polar if there's a polar bond. Otherwise, if we have an atom that has 4 or 5 or 6 atoms surrounding it, no lone pairs of electrons, or 2 or 3. I don't know why I started at 4. I was just thinking about methane, I guess. But if the central atom only has atoms around it, it's going to be nonpolar as long as all of those atoms are the same. And once again, I'm going to give you guys this flow chart, but I just wanted to give you kind of a heads up on how we can decide polarity and dipole moments. So boron trifluoride, BF3. Here we can look at the shape. This is trigonal planar because there's no lone pair of electrons. Since these atoms are the same, fluorine is pulling equally and in an opposite direction. Therefore, these moments, these dipole moments, are canceling each other out. So overall, it would be a nonpolar molecule. Now, if we look at CH2Cl2, we see here's our chlorine atoms, here's our hydrogen atoms. Once again, we have a situation, this is a tetrahedral molecule because there are no lone pairs. It's a 4-0-0 or 4-0-4. So what's happening? Chlorine can pull stronger on its electrons than what The hydrogen can. So we have this dipole moment going towards this chlorine atom, making this side more negative than this side. So this is a polar molecule. Now what happens? If I replace the hydrogens with 2 chlorines, I would become nonpolar. Or I could replace the 2 chlorines with hydrogens. I'd become nonpolar. Over here, if I replaced one of the fluorines with hydrogen, now I'm not equal anymore, and I would become a polar molecule. So I cannot stress this enough that we have to know how to draw our Lewis structures. We have to be able to identify those shapes. And you will be given a shape sheet again, so don't worry. So I look here. This is a water molecule. I notice I have lone pairs of electrons. 2 lone pairs, 2 bonding pairs, 2, 2, 4. This is a bent molecule. Because of these lone pairs, regardless of what the electronegativity difference is here, this is going to be a polar molecule. So there is a dipole moment. If we look at our electronegativity chart, we see that oxygen has a stronger electronegativity, so it's pulling its electrons, pulling hydrogen's electrons towards it, making this slightly negative and these hydrogen atoms slightly positive. Here I have carbon tetrafluoride. Clearly I'm missing quite a few electrons, so please forgive me. So fluorine, 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 fluorine. This is a tetrahedral molecule. All of the atoms are the same, bonded to the central atom. Therefore, this is a nonpolar molecule. Now, fluorine is pulling away, 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 away. So they all cancel each other out. Looking down here, carbon dioxide. Oxygen has a stronger electronegativity, so it's pulling electrons this way. This oxygen is pulling electrons this way. But it's a linear molecule, no lone pairs, which means because these atoms are the same, we see that they cancel out, and it is nonpolar. So no dipole moment. So dipole moment, no dipole moment, yes dipole moment. And simply put, if it has a dipole moment, we just say it's polar. Over here, sulfur dioxide. Oxygen has a larger electronegativity, pulling this way, pulling this way. If we assign our shape, and we don't even have to assign the shape per se, we see that there's this lone pair of electrons here. Therefore, we know that this molecule is going to be polar. If we had sulfur trioxide, so let's say we replace these electrons with another oxygen atom, then we go into a trigonal planar geometry, and the dipole moments would cancel out. So this is polar because there's a dipole moment, and that overall dipole moment is going down in between these 2 oxygen atoms. Ion-dipole interactions. Ion, keep in mind an ion can be positive or negative. Just means that it either lost an electron or picked up an electron along the way. Dipole means a polar molecule. So what happens when we have an interaction between a charged ion, a charged atom, and a polar molecule? So the things that affect this are distance. So the smaller your charge is, or the smaller the atom with the charge on it, means it can get closer to the polar molecule. So distance matters. Size matters here. So the closer you can get, the stronger the interaction can be. We also see that charge. This should be pretty intuitive. The larger the charge, the larger the interaction. So +1 to +2 to +3, something with a +3 charge, first of all, is most likely going to be smaller. So it can get closer, and it has a larger charge on it. So it's going to be a stronger interaction. Also, magnitude of the dipole. So this just means how polar is it? We had that sliding scale of polarity starts at 0.5 and ends at 1.9. So something that's 0.5 is not going to have as much of a dipole as something that has a 1.9, and looking at those electronegativity differences. So the more polar the molecule, the larger the ion-dipole interaction. So we want to be close, we want to have a large charge on our ion, and we want to have a large dipole moment in our polar molecule. And these interactions affect dissolving, enthalpy of solvation. So recall, enthalpy means heat transferred under constant pressure. So what is the energy associated with dissolving something? So this is enthalpy of solvation. And we say enthalpy of hydration when we're looking at water. And we talked about this a little bit when we studied our thermodynamics chapter, and the fact that why is it when you dissolve ammonium nitrate in water, it gets cold, versus when you dissolve calcium chloride in water, it gets hot, right? A heat pack or a cold pack versus a heating pack. So this has something to do with it. And it's very hard to predict whether our enthalpies are going to be negative or positive, exothermic or endothermic. But we can predict whether or not something will be soluble in something else based on their interactions. So a favorable interaction means that we will end up with a solution. So that's ion dipole. And an example of ion dipole would simply be dissolving salt in water. As I said, calcium chloride, ammonium nitrate, or sodium chloride. You make salty water if you want to boil some spaghetti to get that water hotter. So dipole-dipole forces, what does this mean? I have a polar molecule and another polar molecule, water to water. So dipole moment occurs between polar molecules, we've discussed this, and they attract each other electrostatically. So basically what's happening is these molecules are aligning themselves such that the positive end of one of the molecules will be attracted to the negative end of the other molecule. And they arrange themselves to maximize these interactions of the opposites attract rule, right? We're going to keep the negatives away from the negatives and the positives away from the positives, and just try and get as many positives and negatives as close together as we can. So that is what recall means electrostatically. Now, the strength of this intermolecular force is only about 1% as strong as a covalent or ionic bond. And I think in your textbook it lists the amount of energy that is associated with these. And recall that, say for a lattice energy, for keeping an ionic compound together, you're looking at potentially 1,000 kilojoules per mole. Here we're looking on a scale of less than 4 kilojoules per mole. So polar-polar. The more polar these molecules are, the larger the dipole force. As I said earlier, hydrogen bonding is a specific type of dipole-dipole interaction. And the only way you can hydrogen bond is if you have hydrogen connected to a nitrogen atom, an oxygen atom, or a fluorine atom within a molecule. So this is very specific, not chlorine, not sulfur, not carbon, okay? It has to be something like ammonia or water or hydrofluoric acid. Or you can have organic molecules such as alcohols because there is an OH bond. So oxygen has a hydrogen bonded to it. Water is extremely important here with its hydrogen bonding capabilities. And this water has very specific behavior in the fact that when it freezes, when it becomes solid, it's actually less dense than the liquid. And this is a very strange, a peculiar thing about water, because usually solids are more dense than their liquids. And the reason why the solid is less dense is because of this hydrogen bonding. Excuse me. These water molecules actually have to arrange themselves with a specific distance. There is only an allowable distance between each water molecule. So the hydrogen to the oxygen to the hydrogen, this oxygen to this hydrogen. It's an array. And they cannot get too close together. It's not comfortable. So they sit at a specific distance, which is why we actually see water expand when it's freezing. When water's in a liquid form, we don't have to have this set distance because the water molecules are sliding all over the place. They may interact with each other for a moment, but then they're gone. So it only happens when we're freezing that we see how important hydrogen bonding is for water. So when we can dissolve two things that have hydrogen bonding capabilities, we see an even stronger intermolecular force interaction there than just simply polar on polar, okay? Now, another important thing about hydrogen bonding has to do with our DNA, our proteins, our enzymes, all of that. So your DNA, that double helix, is actually held together by hydrogen bonding. So we should really appreciate this about hydrogen and its capability of doing really cool things with nitrogen, oxygen, and fluorine. Now, fluorine, not so much in our bodies, that would be bad. But those nitrogenous bases that are in our DNA that are across from each other are held together by hydrogen bonding. It's a very important intermolecular force. So the last of the intermolecular forces is simply called a London dispersion force. And this is what we call an instantaneous dipole. London dispersion forces are the only possible intermolecular force that can happen between two nonpolar molecules. Because you don't have an ion present, it's not polar, so you can have nonpolar interactions. And it becomes very significant in large atoms or molecules. So an instantaneous dipole moment happens when the electrons will spontaneously move to one side of the atom. So here we see no polarization. Here we see, in our minds, we've got an electron cloud shift, right? Because the electrons are allowed to be in any of those orbitals, moving around at any given time. So in one moment, they can all be on one side of the molecule. When that happens, electrons are over here, which leaves us slightly positive on this side, which then means the atom or the molecule next to it, the electrons would then be attracted to this. And it's kind of like a domino effect. So we see an instantaneous dipole, which then influences the next molecule, influences the next molecule, etc. But it's fleeting. Now, why is it more significant in large atoms or molecules? Well, the larger you are, the more electrons you have. And actually, we can see London dispersion forces being stronger than potentially hydrogen bonding or even polar-polar interactions, dipole-dipole. So London dispersion forces occur in all molecules regardless. So we're going to start to look at, here's this molecule. Tell me what type of intermolecular force it can have. Is it polar? Everything will have a London dispersion force. You can only have ion dipole if you have an ion present. Sodium plus, calcium 2 plus, sulfur 2 minus. That's the only time you can have that, okay? And remember, hydrogen bonding can only happen if a hydrogen atom is on a nitrogen, oxygen, or fluorine within a molecule. So how are physical properties affected by intermolecular forces? So intermolecular forces are, how strongly am I attracted to my neighbor? So melting point and boiling point, we see the same kinds of trends, and that means the stronger the intermolecular forces, or the more you have present, the higher your melting point will be. You have to put in more energy to break apart those associations. Same thing with boiling. Boiling means that you are going to go from the liquid phase to the gas phase. So if your intermolecular forces are really strong in your liquid phase, you're going to have to add more energy to say, hey, I'm going to escape. That's basically what it is. And a liquid molecule has to get enough energy to escape out of that phase and become a gas. So melting point, it's being able to separate those molecules or atoms away from each other. Boiling is you're escaping from the liquid phase into the gas phase. And the deal with solubility is that like dissolves like. I'm sure we've heard that, and why oil and water don't mix. That is because oil is a fat, and it's all nonpolar. Water is a polar molecule. Nonpolar and polar do not mix together. So solubility-wise, if you have the same intermolecular forces, then you will mix well together. I always like to talk about, well, y'all know I'm an Ohio State fan, so I can mix with some other Big Ten teams. I'm similar to them, except for the state up north, which is Michigan. I would not mix well with them. I'm polar, they're non-polar. It's not good, okay? So, like dissolves like. We want to be around similar things in order to mesh well together. Same thing for molecules. So here we can actually compare some boiling points of covalent hydrides, keeping covalent meaning we're sharing electrons, hydrides meaning it's just an atom bonded to only hydrogens. So we look at trends. Chemists love to look at trends and explain, why do we see the behavior that we see? All right, so group 4, we have carbon, silicon, germanium, tin. So we see a normal, what we would expect trend in terms of the boiling point gets larger as we go down the group, simply because we have larger London dispersion forces, because we have more electrons here. So we see an increase in the boiling point as we see an increase in the mass, or the size of the molecule. Looking at group 5, ammonia, okay, so we have nitrogen, phosphorus, arsenic, antimony. This does not follow the trend. Ammonia is higher. Same thing with group 7 here. We see fluorine, chlorine, bromine, iodine. HF has a much higher boiling point, and now we see water way up here, so even higher than fluorine. Group 6, oxygen, sulfur, selenium, tellurium. Why do we see such a change? Why are these higher than when we follow the trend of, well, we're getting bigger, so we must have stronger intermolecular forces? Well, oxygen, fluorine, and nitrogen have that capability of hydrogen bonding. So we see here that the intermolecular forces of hydrogen bonding win out over the size, over, hey, I've got a lot more electrons than you do. My instantaneous dipole may be bigger, but it's not strong enough to counteract what we see with these hydrogen bonding molecules. So generally speaking, the trends would be that the bigger you get, the larger your forces are, therefore a larger boiling point or a larger melting point. But hydrogen bonding wins. So some other properties that we can talk about in dealing with liquids are capillary action, cohesive forces, and adhesive forces. So capillary action is the ability for liquid to travel either into a small tiny tube or simply on a paper towel. If you've ever just laid a paper towel down, you spilled something, you don't want to wipe it up right away, you just set the paper towel down in the puddle or whatever it is that you spilled, and you see that the puddle starts to spread out into the paper towel. That's capillary action, okay? Now, cohesive forces versus adhesive forces. Cohesive means how much are you sticking together. Adhesive forces are how much are you sticking to something else. Okay, so here we see the cohesive forces in mercury are stronger than the adhesive forces to the glass. Over here, we see adhesive forces being stronger because they're more attracted to the glass than they are to themselves, okay? So, and it just has to do, water's polar, the glass is polar, so it's more attracted here. Here we see mercury is nonpolar, so it is not attracted to the glass, it's more attractive to itself. Another couple things in dealing with liquids are viscosity and surface tension, and really I probably should have put surface tension up here. But viscosity is the resistance of a liquid to flow. So you can think about pouring water versus maple syrup or honey. It takes a lot longer for that honey to pour out of the bottle than what it does to pour water. And this is because in your honey or your maple syrup, you have a lot of sugar molecules. Those are big molecules. They have chains associated with them, so they can get kind of tangled up. So that deals with the shape aspect. Intermolecular forces. So the stronger the intermolecular forces, the thicker we see something being in terms of its viscosity, in terms of resistance to flow. They're more attracted to each other, so they don't want to be able to separate. They don't want to pour away from each other. So stronger intermolecular forces, higher viscosity. Once again, the longer, especially things that have a lot of sugar in them, you're going to see a much larger viscosity because of those chains, and they have a lot of hydroxyl groups, which are simply OHs, which means that I have a lot of hydrogen bonding capability. So it all kind of ties in together. Now, surface tension is the resistance of a liquid to spread out. So if you had to ask yourself, how do intermolecular forces come into play? What would we expect? Well, the higher the intermolecular forces, the higher the surface tension, which is one of the reasons why water has such a high surface tension. You can place a pin on top of the water and it won't sink if you do it real gently. Or you see those little water bugs that can walk across the top of water because of the surface tension, because water is so attracted to itself. So here we have what's called a phase change. It's a heating curve, but it shows us our phase changes as we go from, say, solid to liquid to gas, okay? So we can look at how much energy will it take if I want to change so many grams of water into so many, so many grams of ice into so many grams of steam. How do we get there? And at what temperature are we starting and at what temperature are we ending? And when we do this, we notice we have a slope and then we have a flat line. We have a slope and then we have a flat line and we have a slope. So anytime we see a slope, we're going to use the equation Q equals mc delta T. Remember, Q stands for heat. So the mass, the specific heat, and the change in temperature. So how much energy did it take to change a certain amount of ice from negative 20 degrees Celsius to 0 degrees Celsius? Now, anytime we're at a flat line, this is when we're actually going through a phase change. We're converting our solid into a liquid. Whenever you're going through a phase change, there is no temperature change. We stay at 0. We're 0 degrees solid, and then we become 0 degrees liquid. Now, we want to heat our water up to get to where we can boil it. So once again, this is Q equals mc delta T, from 0 degrees to 100 degrees. Now, flat line means how much energy does it take in order for me to change all of my liquid into gas? Liquid at 100 degrees Celsius, gas at 100 degrees Celsius, okay? Then we can see, all right, well, if I want my steam to be 140 degrees Celsius, how much energy is that going to take? Q equals mc delta T. Now, when we go through our phase changes, you're just going to use either the enthalpy of fusion, which is what we use down here, or the enthalpy of vaporization, which is what we use up here. So you have to know the mass, you have to know the different temperatures, i.e. where we're starting, where we're ending, as well as melting points and boiling points. And then you will actually, when we're doing enthalpies of vaporization and fusion, you have to simply convert your mass of your water into moles of water, or whatever subject that we're, or whatever molecule we might be looking at. So this is our heating curve. We can know how much energy does it take to melt this ice cube and actually then turn it into steam. Or we can go the other way. We can start with steam and bring it down to ice, and we don't have to go through all three phases. But notice it takes a lot more energy to go from the liquid phase to the gas phase than what it does to go from solid to liquid. And as we are going up here, we should expect that energy has to be added. So this energy value should be positive. If we were going down the staircase here, then we would expect energy to be given off. So we got to keep these things in mind. So studying phase changes a little bit more here. Once again, vaporization is simply going from the liquid phase to the gas phase. We can also just simply call it evaporation. Condensation is just the opposite, going from the liquid phase, or sorry, going from the gas phase to the liquid phase. Now, if we start and we see, okay, we're condensing, and then we also have a rate of evaporation, at some point we can get these rates to equal each other. And this is what we call an equilibrium. So the rate with which we are evaporating is the same as the rate with which we are condensing. And at this point, we have what's called vapor pressure. So equilibrium just means we have the same amount of molecules going into the gas phase as we have molecules going from the gas phase into the liquid phase. So what is vapor pressure then? Remember, pressure, we talked about pressures with gases, force over an area. So we have an enclosed container here. And under any given temperature, you are always going to have evaporation. Now, the hotter it gets, the more evaporation that we see. Okay? The cooler it is, the less evaporation that we see. But at any point, we can see evaporation of molecules. We start to get so many molecules up here, and then they will start to condense and fall back down into the solution. So when we get this equilibrium, when we get the same amount going up as going down, we say that there is a vapor pressure that is established. And there is a pressure established because now we have basically a fixed amount of gas above the liquid. These are the same substances, though. If this is water, we have water vapor above the liquid phase. So we would talk about the vapor pressure of water in this container. So when we're talking about equilibrium, we're talking about a dynamic function, which means that it's constantly changing. It's not static. We do get a fixed number of molecules that are within the vapor phase, but it only results from the fact that the same amount of liquid is evaporating that is condensing, the gas that is condensing, okay? So intermolecular forces, it's our buzzword, right, for this chapter, our IFs, our ifs. How do our ifs affect vapor pressure? Well, the stronger the molecules are attracted to each other, the harder it is for them to escape. So when we have high intermolecular forces, we would expect a low vapor pressure. And as I stated earlier, the hotter we get, the closer we get to, say, the boiling point, the more vapor that we're going to see. So the higher the temperature, the higher the vapor pressure. So those are directly related, whereas our intermolecular forces have an inverse relationship. So looking here at these three different compounds, water, ethanol, and diethyl ether. Polar hydrogen bonding, polar and nonpolar. There's a nonpolar side to ethanol with polar, so there is some hydrogen bonding here. Diethyl ether is a nonpolar molecule. So what's happening here? At any given temperature, let's look at 30 degrees. Vapor pressure of water's about 30 torr. That's what we're measuring it here, 30 torr. Here for ethanol, it's 100, and for diethyl ether, the nonpolar molecule, we see a vapor pressure of about 680. So higher vapor pressure for the nonpolar molecule, less intermolecular forces, higher vapor pressure. Stronger intermolecular forces, lower vapor pressure. And we also can look at, okay, so we see at 30 degrees, and then if we come down here to 80 degrees, we see that each of these is much higher than what we see at a lower temperature. So at 30 degrees, we were at about 30 torr for water. At 80 degrees, we see that we're at about 340 torr for water. So the higher the temperature goes, the higher the vapor pressure. Now, once we hit what is called our normal boiling points, when we're under standard atmospheric pressure, right? Standard temperature and pressure, or not temperature because we're looking at boiling points, but your standard pressure of 1 atmosphere or 760 torr. That is our normal boiling point. What happens? Well, at the boiling point, this means that our vapor pressure has become in equilibrium. And now all water molecules at that point, at that temperature, are able to escape. Whereas any point below this temperature, we only can see a percentage of them, okay? So when the vapor pressure equals atmospheric pressure, we see that boiling occurs. And these are the respective temperatures for when that happens. Here we have what's called the Clausius-Clapeyron equation. And this equation, once again, scientists, we love to play around with numbers and make lines and graphs because slopes tell us things. And we can make straight lines. We love it. So what can we do? We can plot the natural log of the vapor pressure versus the inverse temperature. So we can measure vapor pressures and temperature, manipulate those so that we can get a straight line. When we get that straight line, our slope is actually equal to the enthalpy of vaporization divided by the gas constant. Now notice here the gas constant has different units because we're looking at energy units, not ideal gas law constant units. So the gas law constant can actually change. And this just simply comes from deriving it in our root mean square speed calculations. All right, so we have vapor pressures, we have enthalpy of vaporization, we have our gas constant, and keep in mind, anytime we're dealing with pressures of gases, we always have to have our temperatures in Kelvin. So what does this equation really allow us to do? If we know different vapor pressures and we know those different temperatures, then we can actually calculate the enthalpy of vaporization for a particular substance. Very useful. How much energy does it take if we want to make this thing boil? All right, moving on to solids. So that was all the stuff about liquids. Moving on to solids here. We have two types of solids, or I should say maybe two categories. We have amorphous solids, which means there is disorder in the structures. There are no regular repeating patterns. Okay, glass is an example of an amorphous solid. On the contrary, we have crystalline solids, which do have an ordered structure. There is a repeating pattern. We see what is called that lattice network, and we talked about that briefly when we studied ionic compounds. And when we look at this, we can talk about unit cells, and we'll discuss what those mean. Now, within classifying our crystalline solids, we have certain types of crystalline solids. We have atomic solids, which are metallic, which occurred through metallic bonding. We have network or covalent atomic solids. So these are all nonmetals. You can have your group 8, so that's your noble gases. Then we have molecular solids, so we have discrete molecules. So this is covalent bonding, but they're only held together then by intermolecular forces. The difference is then between the network or the covalent is it's actually all of the molecule or all of the atoms are covalently bonded to each other. So you can have tons and tons and tons of atoms versus here we have this discrete unit, water versus diamond. And then ionic solids are through ionic bonding. So we aren't talking about intermolecular forces here. We aren't talking about intermolecular forces here. We aren't talking about intermolecular forces here. So looking at our types of crystalline solids, so we have our ionic solids, metal to nonmetal, transfer of electrons held together with electrostatic forces. Sodium chloride, calcium fluoride, ammonium sulfate, these are all ionic solids, okay? Held together, electrostatic forces, very strong. So we tend to see much higher melting points and boiling points for ionic solids, because if you're going to melt an ionic solid, you have to actually disrupt the ionic bond. You have to be able to break that. Molecular solids. So here, molecular solid, we're looking at something like ice, okay? And your molecular solids are much softer generally. So ionic solids tend to be brittle. They also, and we studied some properties of ionic solids and moleculars last chapter. They can conduct electricity when they're melted, but not in their solid form. Same thing with molecular solids. They have a slight ability to conduct electricity when they've been melted. But molecular solids are held together through intermolecular forces. So these are much easier to melt or to boil than your ionic solids. Atomic solids are your diamond, your graphite, quartz, things like that. So we have this array, we have this network here. All of these carbon atoms are actually bonded to each other covalently. So covalent solids or atomic solids are very, very strong. They don't tend to be good conductors of heat or electricity, except for graphite, it's special. But diamonds are insulators. They're very hard, so they have very, very, very high melting points. So we're talking thousands of degrees Celsius. Okay. So here's our description of what these unit cells can look like in terms of our lattices. How are these atoms held together, whether it be within just intermolecular forces, or we're looking at molecules or ionic solids, metals, you name it. So here we have what's called a simple cubic cell, which means that we only have atoms at the 8 corners of a cube, which means that 1/8 of the atom is within the cube. So we would say there's 1 atom per cube. Here we have a body-centered cube, which means that we still have all of our atoms on the outside, but then we have 1 atom in the middle. So overall, there are 2 atoms per cube. 8 times 1/8 is 1, plus the 1 in the middle. Then we also have face-centered cubic, which means that half of an atom is in each face of the cube. So there are 6 faces to a cube. 6 times 1/2 is 3, plus the 1/8 of our atoms on the corners here. So 3 plus 1 is 4. So we have an overall number of atoms in our face-centered cubic equaling 4. So here's some examples. These are metallics. These are metals here: polonium, uranium, gold. How they bond, how they fit together. And we'll actually be able to use the type of cubic cell that we see to calculate things like density and atomic radius. So structure and bonding in metals, and keep in mind, metals are ductile, they conduct electricity well, they conduct heat well, really high melting points, generally speaking. So as I was saying, we can use this information to find density or atomic radius, and we can simply talk about the types of packing that we see, and the packing goes back to what type of cell that we see. And I think the best way to picture this is thinking of, say, oranges and lemons and limes, and how those may be stacked up at a grocery store. So when we have our closest packing, that means we lay down our layer of oranges. On top, we lay down a layer of lemons. And then our next layer of oranges go directly above where the last layer of oranges were. So they're only offset by 1. So it's a 1, 2, 1, 2, or what they say, AB, AB. Okay, so this is our simple cubic cell here. 1 atom per unit cell. Now here we can have our ABCA closest packing. So now we've got our oranges. We've laid those down in a row. We take our lemons, lay those offsetting by 1. So now we've got those. And then we take our limes and put them on top, but instead of placing them directly above where the oranges were, we offset those by 1. So we're sitting in the divots of our layer of lemons that we had just laid down, okay? So here we get a repeating pattern of 1, 2, 3, 1, 2, 3, 1, 2, 3. When we have this situation here, this is what we have when we see our face-centered cubic cell. Now, this shows our hexagonal closest packing. And once again, we have our atoms lying over, our first layer is lying over our second layer. And so we can also see in here, when we've got this layer in the middle, we have the ability then to have 1 atom in the center of our unit cell, allowing us a total then of 2 atoms per cell. So this is our hexagonal. So it's a little different. It's similar in terms of the ABA of closest packing that we saw with just our simple unit cell, but it's really in the way that you draw out your unit cell. How are we defining our limits on our cube is basically what we're talking about there. So here, once again, is another way to look at our unit cell of our ABCA and how we draw our cube here to show that we have, it's hard to see this, it's hard to imagine it in a 2-dimensional plane, but that we have atoms that are on the faces of each side of our cube as well as our atoms at the corners. So here's when we see our unit cell that is face-centered, which means that we have a total of 4 atoms. So once again, just looking a little bit further into those atomic, or what we call network or covalent solids. Here we have diamond, here we have graphite. So the difference between carbon and graphite, we still see this extended array, this extended network of carbon atoms being covalently bonded. It's just how are they bonded to each other? Diamond has a different structure. They're both just carbon atoms, so they're allotropes of each other. So we see some weak bonding, weak intermolecular force bonding there happening between the graphite, which is why you can write with it. It slides. Those atoms are able to slide across each other. Over here we have an example of silicon tetroxide. So here, extensive network of each atom being bonded to another atom, not intermolecular forces here. These are actually covalent bonds. So if we wanted to melt this, we have to break every single one of these bonds. So you can imagine the amount of energy that has to be put in, versus something like water, where it's just hydrogen bonding is associating one water molecule to another water molecule. So as we see here with what we call molecular solids, so your iodine, your phosphorus, your sulfur, carbon dioxide, right, dry ice, and water. So we still see crystalline structures here. We can still look at what type of packing and things that may be occurring. But these are only held together through intermolecular forces, which is why they have much lower melting points and boiling points. Then we look at ionic solids, keeping in mind they're held together through electrostatic forces. And when we look at those packing layers and where we can then fit in another ion, excuse me. So a trigonal hole, we can fit an atom there. Tetrahedral hole has to be in the middle there between these four, right? An octahedral hole, which then sits in the middle of these 6 atoms. So we usually see either the positive ions on the corners, the negative ions in the holes, or on the faces of those cubic cells. And it's really hard to predict whether or not we're going to see an ion in a tetrahedral hole or an octahedral hole or a trigonal hole. It really comes from looking at densities and radii. That's how we can determine whether or not what type of shape or what type of cubic cell these types of molecules have, or I should say compounds, because we're talking about ionic solids. So once again, the important part here about solids is looking at the differences between how are they held together. Is it through ionic bonding, covalent bonding, or is it intermolecular forces? Or for example, with metals, it's a whole different kind of bonding altogether. And then we can look at properties in terms of what's going to have the highest melting point, what's going to have the highest boiling point, comparatively speaking. Well, we would see atomic network solids, you know, your graphite, your diamond, etc. Metals, because those are just simply atoms bonded to each other, not intermolecular forces. So covalent bonds there. Then we look at, okay, next in line are our ionic compounds. Because of that lattice network structure that has to be broken down, we have to actually break those bonds apart. Then we see molecular solids having the lowest melting points and boiling points, because you simply have to break apart the intermolecular forces. So melting points in terms of insulators and conductors, metals are really good conductors of electricity and heat. Generally speaking, molecules, networks, and ionic solids are not. They are insulators, but we do know that if you melt an ionic solid, that you will definitely conduct electricity. So last thing here to look at is what we call a phase diagram. So this is different than looking at a heating curve where we're going through phase changes. That's looking at specifically how much heat do we need to add or remove so that we can change phases. Here, this type of diagram tells us different information about if we're at a specific pressure and temperature, what phase are we going to see? So all that we're concerned with is temperature and pressure. Now, I have a couple things that we can identify. Triple point. So this is the point of temperature and pressure where you see all three phases coexist at the same time. So you have solid, liquid, and gas existing with each other at a specific temperature and pressure. The critical point is that maximum amount of temperature and pressure that you can have where you have a defined phase of either gas or liquid. Otherwise, we get into what we call, it's kind of like plasma. I'll show a video on watching carbon dioxide get to its critical point. And basically what happens is it has the fluidity of a liquid, but it has the density of a gas. So it's no longer liquid or gas. It's a critical fluid, basically. So our critical temperature and critical pressure are the points, that last point, kind of the point of no return, where that occurs. Now we have our phase equilibrium lines, which means that at any given temperature and pressure along that line, we will see just two phases existing. And that means then we are either melting, or we can be boiling or subliming, things like that. And sublimation just means going directly from the solid phase to the gas phase. So comparing water and carbon dioxide, two different phase diagrams here. It's always important to look at what's happening when our pressure is 1 atmosphere, because that's our standard pressure. It's what we call our normal boiling point. Our normal melting point is when we are at 1 atmosphere of pressure, what is the temperature with which we can either melt something or boil something. So as we know, temperature melting, normal melting point, 0 degrees Celsius. Normal boiling point, 100 degrees Celsius. Here we have our triple point existing at 0.0060 atms, very small pressure, and a very low temperature, 0.0098 degrees Celsius, less than a degree Celsius. So at this point, we see solid, liquid, and gas occurring all at the same time. So over here, when we're in this area, if you are in any temperature and pressure that leads you to be a point in this area, you are only a solid. Here, you are only a liquid. In this area, you are only a gas. Now, along this line, separating solid and gas means that I'm in equilibrium. So I have both solid and gas existing at the same time if I have this temperature and pressure. Here, if I pick a temperature and pressure on this line, then I am in equilibrium, solid and liquid, which means I'm either melting or freezing. If I'm somewhere along this line, that means that I'm in equilibrium between liquid and gas. So I'm either boiling or condensing. And the two terms that we use down here, solid to gas, sublimation, gas to solid, deposition. And deposition, a good example of this is frost. So whenever you wake up and you see frost on the grass, that is an example of deposition, because the water vapor froze. It was a gas, it became a solid. So over here, we have a different set of conditions. 1 atmosphere pressure, the melting point for carbon dioxide is -78 degrees Celsius. Here, our triple point is at 5.1 atmospheres, so much higher pressure, but much lower temperature, -56.6 degrees Celsius. I forgot to mention over here, our critical point occurs for water at 218 atmospheres, so under extremely high pressure, and a temperature of 374 degrees Celsius. So out here then, we're that critical fluid. So here the critical point, 72.8 atmospheres, only 31 degrees Celsius. So we have our three phases. These are the way the phases always go, solid, liquid, gas. Because the hotter you get, you go from solid to liquid to gas. So left to right, we always see solid, liquid, gas. Now notice the difference between these two phase diagrams in terms of the slope of the line between solid and liquid. Here we have a positive slope. We're leaning to the right. This means that the solid is going to be more dense than the liquid. Here, our slope is negative, or we can just say leaning to the left, which means that our solid is going to be less dense than our liquid. So ice, solid water, floats on liquid water. Here, solid carbon dioxide would sink into liquid carbon dioxide. So this is what this line tells us. But the lines still mean the same things in terms of this is our equilibrium here between solid and liquid. This is our equilibrium points between liquid and gas. Here's our equilibrium point between solid and gas. So within this chapter, main thing with liquids is how do we determine our IFs, our IFs, our intermolecular forces? They are so important to figure out how to say this is ion dipole, this is dipole dipole, this is London dispersion, this is hydrogen bonding, because those properties that we looked at for liquids, vapor pressure, melting point, boiling point, solubility, surface tension, viscosity, adhesive forces, cohesive forces, surface tension, all of those are affected by intermolecular forces. So you have to know how to draw those molecules, know the shape so that you can identify the intermolecular forces, and then you can relate strong intermolecular forces means high melting point, high boiling point, low vapor pressure, high surface tension, high viscosity, et cetera, et cetera. Okay, so then we looked at solids. So we looked at the categories of solids, amorphous versus crystalline, and then we studied the different types of crystalline solids, and we will actually do some calculations with densities of metallic solids and atomic radii using the information of cubic unit cells. And once again, then we also studied the properties of melting point, boiling points for those different types of solids. So we have atomic or covalent network. Those mean the same thing. We have ionic, metallic, and molecular. So make sure you guys study, read the book, and work on those homework problems. All right, good luck.